Good morning, 12th graders. Please excuse my voice. I've been losing my voice. But we are moving on in this lesson. We started out with interpreting exponential models. We started out by looking at the equation and being able to understand what we're looking at when we see an exponential model. And now we're going to transition into how do we create an exponential model. Now, this is not our first unit where we've been creating models, right? We did linear a long time ago. We did quadratics at the beginning of the year, and then we did cubics. And so we always had this system of creating models where we were making a system of equations, right? If we had three unknowns, we need 3 points in order to make three equations, which would make a system of equations. This is where with exponential models, it gets a little bit tricky. You can't always make exponential systems of equations because if you go into your calculator and take a look at the function that is, let me get that brightness up. If you go into the function that we use, which is systems of equations, right? Notice it says systems of linear equations. So just keep that in mind as we go through here. Let's get started. Megan forgot her coffee on her desk. A student measures the temperature of her cup at regular intervals in the classroom where the temperature is 20 degrees. Why would they tell us that? I don't know, but they never are trying to trick us, so let's just keep that in mind. The table to the right shows the data. So we know with exponential models that there's this general idea of either the shape is going to be something like this or the shape is going to be something like this. And as you're taking a look at this numerical representation, try to think about like which of these two would it be, right? It tells us that it's an exponential model. It gives us this form and we take a look and we see that as time moves on, and we can think about it, as time moves on, the temperature is going to go down, right? And so this is going to be more of the model that we're looking at. So it says to develop an exponential model. Now, this is what I was talking about a couple minutes ago, where I'm saying we have 1, 2, 3, 4, 5 sets of points, right? And we have one unknown. E is just a number, so it's not a variable, right? It's a number, just like pi is a number. So we've got an unknown of k, we've got an unknown of r, and we've got an unknown of c. X is supposed to be x, f of c, f of x, y is supposed to be y. E is just a number. And here they're trying to further emphasize that by saying like, hey, K, R, and C are our unknowns. And so that's what we're trying to solve for. And we have more than enough points in order to solve for 3 unknowns. We have 5 points for 3 unknowns. We're golden, right? But if we start to see, when we start to plug in things, we can plug in 0 and 95. So 95 would go in for Y equals k times e to the r times 0 plus c. We can simplify this down. Er times 0 is 0. And then anything to the 0 power is just 1, right? So that's 95 equals k times 1, which is just k, right? So, okay, we've plugged in the point 0.95, and that's awesome. We were able to simplify it down to be able to have an equation that involves K and C, which is nice. Now, here's where things get tricky. If I plug in 79 equals K times E to the R times X would be 1. So I'm just going to keep it as R and not write 1 because R times 1 is just R plus C. This is where we can see that we can no longer use the system of equations in our calculator, which is a bummer, because we're raising something to an exponent. And so that variable being in the exponent no longer is a linear equation. So because we have a variable in the exponent, we no longer have a linear equation. We no longer can use the systems of linear equations on our calculators. So with exponential models, unfortunately, the system that we've been really practicing kind of goes to the side. So we have to be a little bit more creative about creating these models. So we're creating some equations. This is linear. Notice no variables in exponents. Nothing's being squared or cubed either. So it's all good. It's all linear because all the exponents are 1. So that's actually good for linear equations. However, this is starting to be not good. So what do? We start to try and hone in on important things that we're given. This is an important thing that we are given. If we think about a coffee being left out on the desk, the coffee will never go below the temperature of the room, right? We don't cool things by leaving it outside, right? Like if I wanted to freeze ice, I wouldn't put it in a room. I would put it in an environment in which it is colder than the room temperature. So then that way you're bringing the water to the freezing temperature that is the ice box, right? The refrigerator, the freezer. So when we think about setting coffee on a table or setting anything into a room situation, you're slowly bringing that temperature to room temperature. And so when we think about the idea of an exponential model, there's always going to be this horizontal asymptote. And in this case, the room temperature would be our horizontal asymptote. The temperature is slowly approaching, or quickly at first, and then slowly approaching that room temperature. And so we're bringing the coffee temperature to the room temperature. And that's what our horizontal asymptote is. And if you remember, what variable in this situation, K, R, or C, which of these three variables is going to represent our horizontal asymptote? If you don't remember, you go back to the first page, which is not written here. So let me grab my my completed version that I have right here. If we remember, C is our horizontal asymptote, right? A plus C. So you can go up to here, plus C. That plus piece at the end is our horizontal asymptote. So that means for this guy as well, C will be our horizontal asymptote. So that tells us that C is equal to, if the temperature is always approaching 20, C is equal to 20, which is super helpful. If I know that C is equal to 20, then I can go over here and say, C is equal to 20. So 95 equals K plus 20. You could numerical solve, or you could just subtract 20 from both sides and say that 75 is equal to K. So I have my K, I have my C, and that means I've solved for I've solved for 2 out of the 3 unknowns, right? None of it was a system of linear equations. None of it was like us having to put something into our calculator. This process is still a system of equations process. It just looks slightly different than what we've done. We have to kind of puzzle out what goes where in order to start eliminating things. And if I hadn't have plugged in this point at the beginning to be able to figure out that relationship, and then got stuck, right? The getting stuck in the maze that is this problem solving that we're doing, then I wouldn't have been able to so easily be able to figure out K right after I'd figured out C. So all of the problem solving processes that we go through are important. Now that I have C and I have K, maybe I can take this guy and put it over here and see if I can solve, right? So I've got 79 equals 75 times e to the, I still don't know what R is, but I do have plus 20. At this point, I can plug this into numerical solve. The reason why I can plug this into numerical solve is that I only have one variable, right? E is just a number. So if I have just one variable left in the equation, I can do numerical solve. If you have a TI-84 instead of a TI Nspire or a Casio, you would have to subtract 20, divide by 75, and then take you would do log pieces. If you have a Casio or a TI-84, come and talk to me in class and we can talk about how we would solve this by hand. But instead, we're going to do numerical solve. And numerical solve is going to be 79 equals E. So this is why I'm not going to ask you to do this on your own. E is right here, E to the X. It's a number, right? It's right by X squared, E to the X. So I'm going to press that button, and it's already done E to the, and then I'll put R because I want to stay consistent, but if you wanted to put X, you're totally fine. plus 20, comma, R. Press enter. Echo. So R is approximately negative 0.2. Ooh, this one's a tricky one. 39951. If I wanted to do 3 sig figs, 240. But if you don't want to do 3 sig figs, then you could just leave it like that. Now that I've solved for all of these pieces, I've planned, I've solved, I now need to assess. Did I answer the question I was asked? So I look, develop an exponential model of the form this. So have I created the exponential model? No. In other words, I need to write the equation. The question is asking me to write the equation. I've done all the pieces that I need to do in order to write the equation, but let's make sure I actually answer this question I'm being asked. So f of c equals 75 e to the negative 0.240 x plus 20. Boom. If you also wanted to do one further step to check, a really great way to check is you could graph it. Whoops. Here we go. I don't see it at first, so I'm going to do zoom fit so I can start getting it into the window. It looks like how it's supposed to look, right? Like we know it's supposed to like be a temperature that goes down over time. And I want to check that I've made the correct equation. So check my table values, right? If I do graph trace, is it 95 at 0? It is 95 at 0. At 1, is it 79-ish? Yeah, it is. At 2, is it 66.41? Yeah, it is, right? So this is a really great way that you can double check. If you're ever unsure when you've created an equation, you could always just, hey, here's your table, and you can double check. And I needed to do this anyway because it says use your model to find the temperature after 8 minutes, right? Find the temperature. So, okay, temperature is F of C equals what? 8 minutes means C equals 8. Go ahead and solve. I would use your graph if you've already done it. Just do graph trace. I'm already on graph trace. So if I type 8, enter, right? If I have the x value, I can solve for the y value. If I have the y value and need the x, it's slightly different, but it's okay. 8 gives us this guy. If you have less sig figs on your graphing calculator than I do, you might have gotten 40.0, or sorry, no, 31.0 or just 31. It's because it was rounded by this like pretty darn close to 31. But I'm going to do